Welcome back again. This is going to be episode number 35 of Learning by Doing MPI and part number 7 of virtual topologies in MPI. We're going to continue from where we left off last time. We talked about this MPI neighbor all gather, but we didn't have time to basically take a look at the code examples themselves. So we have 3 examples here. The first one is MPI neighbor all gather.c. So MPI neighbor all gather.c. So I'm not going to comment on these because we have seen these like in hundreds of our examples. First thing to notice is that what kind of communicator do we have, or what kind of virtual topology we have on top of our communicator. And you can see that we are using this topology constructor that is a distributed graph using the adjacent variation. If you remember from previous episodes, distributed graphs had 2 constructors. One was this adjacent, and the other one was the most general one without this suffix at the end of the command. So with the adjacent, you remember that we're basically responsible to determine what are the incoming and outgoing sort of edges for the current process. So that is the process what we are doing right here in this section of the code by specifying in degree, out degree, sources, destinations, and this reorder is basically whether it's allowed or it's not allowed. But you can see from place to place, we have written ring topology here. What do we mean by that? So maybe the best way is for me to draw something for you, but apologies because I cannot draw like nicely with this sort of touchpad, but I try my best. So I'm gonna reduce the size. So let's say these are sort of representing 4 MPI processes. So, and now consider the middle process. So we're gonna, this middle process is gonna send information to the process before. So this is the direction of data transfer. And to the process to the left, or process before, and to the process after, or the process to the right. And it's going to receive information from the same processes that it sends data to. So from process before and from process after. So this is basically called a simple ring topology. That every process is going to have 4 sort of communications. 2 of those communications are going to be send operations, which the current process is going to send to the process before, data to process before, and it's going to send data to process after itself. And it's going to receive data from process before itself and from process after itself. So this is sort of a ring topology. So in the case of our example, we have 8 processes. So imagine that this middle process is process 0. So I'm going to take this out and take this 0 up to here. So imagine that this middle process, this dot here, or this circle here, is process 0. In the scenario of 8 processes, our processes are going to be ranked from 0 to 7. So what's going to be the process before process 0? It's not process -1. We don't have process -1. But in turn, we're going to have process 7, the last process. So this is going to be process before, and what is going to be process after that? It's going to be process 1. So these dots, the process before is going to be 7, and the process after is going to be 1. So this is a ring topology and a visual representation in the case of, for example, rank 0 or the root process in the case that we have 8 processes. So now let's take a look at that. So we have in degree of 2, so this means that our current process is going to receive 2 items from 2 other processes, and it's going to, out degree of 2, it's going to send data to 2 other processes, and source is going to have the same sort of size as in degree, and destination is going to have the same size as the out degree, and the reordering is not allowed. And then when we want to mention the rank of the sources and destinations, you can see, for example, here, this is process before and this is process after. But why do we use this formulation? We can try it out. Let's say for root process, if rank is 0, Then 0 plus 8 is going to be 8, minus 1 is going to be 7, 7 modulo 8 is going to be 7. So that is process before, right here, this one. And that is why I put this comment as process before. And this formula, you see 0 plus 1 is going to be 1, 1 modulo 8 is going to be 1. So then that's process after. This is this one. So, and then for destinations, we do the same. We use the same formulation for process before and process after. And this is where basically the magic happens. These few lines of code, neighborhood collective communication happens here. The send buffer is the rank of every process. So every process is going to send one integer, and that is the rank of itself. And the receive buffer is going to be an array with the size of 2. And the reason is obvious because we said we have this ring topology and we're going to collect two integers from two neighboring processes, from process left and process right. And we initialize this receive buffer with values of -1 and -1 because if something basically happens or if a mistake is happening, then we immediately know that our receive buffer, when it is -1, it means that there was no sort of communication in that direction, right? So now we use MPI neighbor altogether. We basically pass in all those proper arguments. And then every process is going to print its own receive buffer along with its own rank. And then we do some freeing. So let's run this example, MPI cc MPI neighbor altogether.c. MPI run, it was, how many processes? I think it was 8, right? So now you see that process 0 gets these ranks, 7 and 1. 1 is between 0 and 2 is between 1 and 3, and so on and so forth. Now you see how beautifully we basically showed the use case of this MPI neighbor altogether. So this was syntax and semantics of this function. But in the first example, we used a distributed graph and with the adjacent sort of topology constructor. Now let's take a look at the version 1. That's MPI neighbor altogether in V1. The first version, again, these things, we already have seen them like hundreds of times. Let's see what kind of constructor we have used here. This one, MPI cart create. So this example shows the usage of MPI neighbor altogether with a Cartesian grid. And we already mentioned that in the standard, it says that right here, this procedure supports all of the virtual topologies that we have at our hand, Cartesian communicators, graph communicators, and distributed graph communicators. It supports all of them. So the second version, or the first version actually, V1, shows a three-dimensional Cartesian grid. You see it here. And you see that we have periodic conditions in all dimensions or directions. And this is the comment that I put here. So try 3 in the middle. We can ignore this because I copied and pasted this example from the earlier versions. So you can ignore this comment. But anyways, we are using MPI dims create. And you know that since we are passing 0, 0, 0, then it's going to be in non-increasing order. So it's going to end up, in case of 12 processes, it's going to be 3, 2, and 2. That multiplication is going to be 12. So we're going to have a three-dimensional structure, Cartesian structure, and then we are trying the same thing. We're sending our rank, but wait a second, why our receive buffer now all of a sudden it's having 6 elements, or the space for 6 elements, and we have initialized them again. And you see that I put a comment here, from above, below, left, right, and front and back. I actually need to add that as well. So this should be front and back. Or actually, I need to put a comma right there. So front, back, above, below, left, and right processes. So now you kind of get the idea, but the best scenario is, again, let me try to draw something here. Let's say this is a molecule. This is my graph, a process in the middle. So these are the processes, left, right, top, bottom, and this is back, and this is front. So I cannot basically represent a 3D structure here, but I try my best. So this is going to be process above, process below, process before, process after, and process before. That's sort of a computational molecule. So ideally, every process in a Cartesian grid is going to have 6 neighbors: top, bottom, left, right, front, back. So I tried very badly to basically draw that, but I think you get the idea. So that is why we have sort of a space for 6 integers, because we only are sending one rank, which is an integer. But for the receive buffer, we're going to receive it from the neighboring sort of edges that we have, which ideally is going to be 6 of them for a perfect molecule, sort of completely inside a Cartesian grid. And then every process basically prints all those receive items. And then we have this freeing in the end. We need to free the communicator. So let's try to run this. MPI neighbor all gather v1.c. And this case, we need to run it with 12 processes, if I'm not mistaken. Yeah, so this information we have seen before. And you see, for example, in the case of process 0, we have received 8. So process 0 has coordinates of 0, 0, 0. Communication starts with row major first, so row-wise. The process or the element before 0 is going to be -1. But since we don't have any -1 process, and we have periodic conditions, it means that it's going to be the last process with this 0th element. So it's going to be 2 for this element and 0 and 0. So where that is, 2, 0, and 0 is right here, and that is process 8, right here. The process after this is going to be 1, 0, and 0. Where is that? It's right here. 1, 0, 0 corresponds to process 4, and that is why we have process 4 here. Now we go column-wise. So what is the process before? It's 0, -1, 0. But since we don't have any -1, it's going to be the last process in the column. So it's going to be 0, 1, and 0. Where is 0, 1, 0 is right here. That is process 2, right here. What is the process after this? It's going to be 0, 1, and 0. That is why we have a sort of repetitive pattern of 2 and 2. And this one is for the depth. This is for the last element. So you see, what is the process before? It's going to be 0, 0, -1. No, we don't have any of that. Since we have periodic conditions, it's going to be 0, 0, and 1. So what is 0, 0, and 1? It's right here. It's process 1. And what is the process after this? It's going to be 0, 0, and 1. Again, we're going to end up with 1. So that is why we have 8, 4, 2, 2, and 1, and 1. And why do we have these rank values? Because the send buffer was simply the rank. So we are sending the rank of every process to other processes. So I think with that example, you basically get the idea. And the last example is version 2 of this. So we have seen it in a distributed graph with adjacent. We have seen it in a Cartesian grid. Now let's take a look at the last one and see what the last one is all about. Oops, neighbor all gather v2. Okay, this one seems like we have seen this pattern, right? This is the one that process 0 was in connection with process 1 and 3, process 1 with 0, process 2 with 3, and process 3 with 0 and 2. I think this pattern was from example 8.2 in the standard, if I'm not mistaken. This should be in example 8.2 in this standard. Let me take a look at it to make sure that it is actually that case. This is 8.1, that example. 8.3, and this is 8.2. Where is 8.2? No, I cannot seem to find it. This is... Oh yeah, here, right here. So you see that 1 and 3, 0, 3, and 0 and 2. This is exactly the same pattern that we had here in this example. Now we got to go back to the page. I think it was 453 right here. Yeah. So we have that pattern. So you already know what's going on here. And then we are using the general case of MPI this graph create. This is not a JSON. This is this graph create. And then we are using this inquiry functions. We do some stuff. We print some stuff as we printed it before. So you already know this code because in previous episodes we saw this topology constructors already. And then we put a barrier to basically make sure that things are printed in order. And then this is where the magic happens. Neighborhood collective communication. Send buffer is still the rank of every process. And then the receive buffer is going to be 2, and we're filling it up with -1 and -1. And then we are basically printing this. So this example is very, very similar to the first one that we had with a JSON version. But let's take a look at the difference. MPI CC, MPI neighbor all gather, whoops, v2. And I need to run it with, was it 4 processes? Yeah, so the main difference is that in this case, you see -1 and -1 for processes 1 and process 2, right? Now, going back here, I just passed it. I passed the example 8.2. But you remember process 0 had 2 connections, 1 and 3. Process 3 had 2 connections, 0 and 2. But in this case, process 1 and process 2, they both had 1 connection. And the connection was 0 and 3 in this case. And this is -1 and -1 because the receive buffer hasn't received anything. And since we initialized the receive buffer with -1, you see that -1 is getting printed here. So of course, what we could do is, I actually don't like to mess up with my original code. I'm going to keep this like that, but let's copy this then. MPI neighbor all gather. I want to show you. So v2 into test.c, and this is the same example, but I'm going to put it in test because I want to change some stuff here to show you that if you're not happy with that -1, you can see that instead of putting this 2 here, I can put in degree because that is sort of the amount of data that I'm going to receive. So I can put in degree right there. I can do the same, basically a communication. I can get rid of this one. Whoops. And then I can say printf proc %d received the same message as before. Nothing crazy is happening here, and passing the rank right there. And what I'm going to do is to put a for loop with an integer I from 0, I less than in degree, and then I++. And then what I'm going to do is to print basically %d with a comma, and then that's going to be my receive buffer of I. And then, of course, I made a mistake here. This should be -1 because I want to print the last one without a comma. So I'm going to put here a %d and a backslash or slash. I always mix them up. And this should be receive buffer of in degree -1. That's the last sort of element. So if I do that, now you see that this time we don't have the size of 2 for the receive buffer, but everybody is going to get its own size of receive buffer depending on the in degree. For every process, the amount of data you receive is determined by the in degree. And then here you print it with this sort of pattern. And now if I say MPI CC test and I try to run it with 4 processes, now you don't see that -1, that annoying -1 here. But for the other processes, you see the information that is being sent with a comma and then the last one which basically appears. For process 0, you see that we have 1 and 3. With process 1, we only have 0, and for process 2, we have 3. And for process 3, again, we have 2 and 0. So this is another way. So I'm going to remove that. So if you don't feel happy with that -1 appearing in the as a result of initialization of the receive buffer, Or if you don't want to basically have receive buffer with the maximum size of the available sort of communication, then you can use this solution that I just typed in test.c. So this was 3 examples that we saw. The first one was in the case of distributed graph with adjacent. The second one was a Cartesian grid, and the last one was a general case of MPI distributed graph. And the last one was sort of a replication of example 8.2 sort of pattern with those 4 processes. Yeah, now we can move on to the next sort of, we have read all these information before, and we know what all these things are. So the next one on the line is basically, let me put this one here. The next one on the line is MPI neighbor all gather V. So this is the vector variation of this one, and the difference that it has is that, again, everything is going to be an input and the receive buffer is going to be the output. What is the difference between this one and the all gather version? So the V version basically gives you this flexibility. It gives you displacements. I'm going to use this one. Yeah, this is better. So it gives you displacements, and the displacements you can see it's an integer array with the length of in degree, of course. Why? Because the receive is happening in the current process is the number of in degree. So we're going to get from in degree sources that type of data that they are sending to us. So displacement in this case is going to be an array. You can see also the C bindings. So your receive counts is going to be an array. It's not, take a look at this. Your receive counts here is just an integer, but in the case of the vector version is an array, is an array of integers. And then you see that your displacements is also going to be an array of integers, and the rest of the arguments are going to be the same. So in this case, it basically gives you more flexibility. Now receive counts is simply an integer array of length of in degree again, containing the number of elements that are received from each neighbor. So it gives you more flexibility in this case. So of course I made a mistake, so I need to add here, what kind of examples do we have here? MPI neighbor all gather V. So we have all gather V and V1. I need to add it, sorry. CMPI neighbor all gather V dot C and MPI neighbor all gather V V1 dot C. So that's, I forgot to put that one there. Okay, so now jumping here, let's take a look at this one. The first example, we're not going to talk about this. Again, 8 processes are going to be used. You see that this is similar to previous example. It's a ring topology with the same sort of ordering and everything. And we're using, again, this distributed graph adjacent. But the changes are made here, which is the neighborhood collective communication. In this case, again, our send buffer is the rank. So everybody sends 1 integer. And then the receive buffer is going to be 2, again initialized with -1 and -1. Displacements is going to be 2, and receive counts is going to be 2. And then we put a for loop here to put displacements to be 0 and 1 because we have 2 elements. And for receive counts, for both of them, it should be 1 element because every process in a ring topology is going to send 1 sort of data. And then we use MPI all. MPI neighbor all gather V, you see the difference, it's the vector version. And then we pass in sort of, you know, the proper arguments, receive counts, displacements. And you kind of also notice, whoops, the 25 minutes mark is over. I'm going to finish this and then we're going to continue in the next episode. So now you see the difference that displacements and receive counts is sort of not a single value, but it's sort of a integer array. And every process basically prints the same thing. So essentially this should be more or less the same as before, but with this all gather V version of stuff. Let's see. And MPI run minus NP8 processes, if I'm not mistaken. And yeah, so now you see we have the same results, as process 0 is between 7 and 1, and process 1 is between 0 and 2, process 2 is between 1 and 3, and yeah. So we're going to see the version 1 of this example in the next episode.